Today, we're going to look at how you can manually calculate an azimuth of a star using a nautical almanac. So firstly, what is an azimuth? If we look in the dictionary, in navigation an azimuth is the arc of the horizon measured clockwise from the northern point to the point where a circle through a given heavenly body intersects the horizon. In normal words, it's just a bearing. The different name comes because we need a way to differentiate between the different numbers that we use measuring celestial bodies. When you calculate the azimuth of a celestial body, you're just calculating its bearing from your position. So, first off, we're going to need a set of starting information before we can even enter the almanac. We're going to assume a position of 27 degrees, 10.2 minutes north, 043 degrees, 35.9 minutes west, which places us somewhere in the middle of the Atlantic. The date, we're going to say, is February the 16th, 2018. Our local time is 03:30 and 15 seconds, and our time zone is UTC-3. This means that we're going to need to add 3 hours to our time to get to universal time. So it's 06:30, 15 seconds, universal time. The star that we're interested in is Vega. Now the method for actually selecting the star is beyond the scope of today's tutorial, as we're just going to be looking at calculating the azimuth itself. With that information we can then enter the almanac. As always, we will be using the almanac available from thenauticalalmanac.com, so you can head over there if you want to get your own copy. First off, we need the daily pages for our date. So in our case it's pages 32 and 33. Now there are a few things to note here. Notice for Aries, Venus, Mars, Jupiter, Saturn, the Sun and the Moon, we're given tables for the Greenwich Hour Angle, or GHA. But for all the stars, we're instead given this table with SHA, or Sidereal Hour Angle. So what's the difference? Notice how the Greenwich Hour Angle table gives values that change hourly, but the Sidereal Hour Angles are fixed. The Sidereal Hour Angles are just a way of linking every star to this first column, Aries. What it means is that the almanac can tabulate hourly values for Aries, and then you can transform them using the sidereal hour angles for each star. Now that you know that, you also know that we're going to need to pull the data for Aries as well as the data for our star. Looking at the table for Aries on Friday the 16th, we can pull out the value that corresponds with the time that we need. As with everything in the almanac, we use universal time, so we're going to need row 3 for 03:30. This gives the Greenwich hour angle of Aries as 191 degrees, 03.6 minutes. We're then going to need to use increments to get to 30 minutes past the hour. So we're going to turn to the increments and corrections pages. Depending on your almanac, this will either be within the almanac itself or it may be a separate document. If you're using the same almanac as me, it's a separate document but it's still available from thenauticalalmanac.com. I want the page for minute 30. Each minute has its own table of corrections. Minute 30 is here on the left, with each row of the table representing 1 second. As we need 30 minutes, 15 seconds, we look at row 15 in the 30-minute table. We find our correction is 7 degrees, 35.0 minutes. We can then apply our increment to the 0300 Greenwich hour angle to get the Greenwich hour angle of Aries at the precise time that we need, which is 198 degrees, 38.6 minutes. Now, the Greenwich hour angle doesn't have a label, it's not labelled east or west. Let's have a look why. Let's take the Earth. If you look down on the Earth, straight down at the North Pole, and you line it up with Greenwich, or the prime meridian, at the top, you can follow around clockwise and you move west. Follow around anti-clockwise and you move east. Greenwich hour angles are measuring clockwise from Greenwich, or the prime meridian. It's just a way of referencing bodies on the celestial sphere. We've calculated Aries as having a Greenwich hour angle of 198 degrees, 38.6 minutes, which is just round here. Aries is on the celestial sphere, which is fixed. As the Earth turns, the Greenwich hour angle of Aries changes, simply due to the rotation of the Earth. The Greenwich hour angle is always increasing as the Earth turns. This is why you always add the minute and second increments to the hourly value from the almanac. where we're given the sidereal hour angle of a star is just a fixed distance from Aries. A sidereal hour angle of 0 degrees would line up the star with Aries. 90 degrees would place the star here, 180 would place it here, and 270 would place it here. Stars are effectively fixed on the celestial sphere, so they always maintain the same position relative to Aries. In truth, they do move, but it's insignificant for our purposes. As the Earth rotates, the position of each star changes, but it's the exact same amount as the position of Aries changes, hence the use of sidereal hour angles in place of tabulating every star individually. When you add the sidereal hour angle of a star to the Greenwich hour angle of Aries, you may get a number above 360. If so, you just need to subtract 360 to remove that extra lap of the Earth that you've done in your measurement. So let's have a look at our star. We find the sidereal hour angle of Vega is 80 degrees 37.1 minutes. To find the Greenwich hour angle of Vega at 03:30:15, we add the sidereal hour angle to the Greenwich hour angle of Aries at our time, which we already calculated as 198 degrees 38.6 minutes, and we find the Greenwich hour angle of Vega is 279 degrees 15.7 minutes. But for our calculations, we actually want to turn that Greenwich hour angle into a local hour angle, or LHA. The easiest way to explain this is to look at our diagram again. We can plot the Greenwich hour angle of our star, and also mark on our own position. Our longitude was 43 degrees 35.9 minutes west, which places us here, just over 43 degrees clockwise from Greenwich. Local hour angle is the angle between us and the star. As our longitude is west, we just subtract our longitude from the Greenwich hour angle of the star to find the angle between the two. Of course, if our longitude was in the east instead, we would need to add it to the Greenwich hour angle of the star. Again, if the resultant is greater than 360, just subtract that 360 to eliminate the extra lap of the Earth. So, in our case, we find the local hour angle of Vega is 235 degrees 39.8 minutes. The only other data we need is the declination of Vega, which you probably spotted already. You read it directly from the star's table. 38 degrees 47.9 minutes north. Some almanacs will write north. In our case, we know that north are the positive numbers. If it's negative, then it would be south. And now we come to the calculations. I use the ABC method, which matches publications like Norrie's tables, which you could use if you didn't have a calculator. I just use a calculator to give me the values instead of looking them all up in the tables themselves. The formula for finding A is tan of the latitude divided by tan of the local hour angle. If you use the A table in Norrie's, it would give this to 2 decimal places, but I like to keep full precision and just write 5 decimal places instead, so I get 0.35061. A is labelled as the opposite of your latitude, unless the local hour angle is between 90 degrees and 270 degrees. In our case, local hour angle is 235, so we label A as the same as our latitude, so it becomes 0.35061 north. Now B. B is found using tan of the declination divided by sine of the local hour angle. Again, you could read this straight from Norrie's. I use my calculator and I find B equals minus 0.97364. You actually just ignore the minus sign as we work out what to do with it in the next step. The label for B is going to be just the same as the declination, it's always the same. So we get 0.97364 north. For C, we need to look to both the A and B values that we've calculated. If the labels on them are the same, we're going to add them together. And if the labels are different, we're going to take the smallest one away from the biggest one. C is labelled as the same as the biggest of either A or B. In our case, both are north, so we're going to add them to get C is 1.32425 north. Finally, we can use C to find the azimuth. Again, you could use the C table in Norrie's. Azimuth equals the inverse tan of 1 divided by C divided by cos lat. Make sure you just put it through the calculator as it is, all at once, to maintain the accuracy. So I'm going to type 1 divided by 1.32425 divided by cos of 27 degrees 10.2 minutes. And then I'm going to inverse tan the result, and I get 40.3 degrees. Now, labelling this value is a little trickier. It needs a north-south and an east-west label. North-south is going to be the same as C, so that's easy. In our case, it's going to be north. East and west depends on the local hour angle. If the local hour angle is less than 180 degrees, the label is going to be west. If it's greater than 180 degrees, the label is east. So in our case, we're going to write azimuth equals north 40.3 degrees east. To turn that into a bearing, we need to use another diagram. The first label is where to start the bearing, and the second label is where the bearing goes towards. For us, we start from north and head east 40.3 degrees, so the azimuth is going to be just 040.3 degrees. Had it been north something west, it would describe this angle, so the bearing would have to be 360 degrees minus the angle. South something east would be this angle, so you do 180 degrees minus the angle, and south something west would be 180 degrees plus the angle. But you'll get used to this notation the more you practice. So now you've completed the full calculation for the azimuth of a star. You can follow the same process for calculating the azimuth of any star from any location. In future videos, we're going to start to use that azimuth to help us in navigation.